everyone. I'm Rob Slater, co-founder of Redshift Rendering Technologies. We formed our company in 2012 with 3 video game industry veterans. We launched our first alpha in March 2013, with version 1 following a year later. We've not done any effort in marketing so far, so you'll be forgiven for never having heard of us. So, what is Redshift? Well, Redshift is not just another GPU renderer. It is a final frame, production-ready renderer that brings the flexibility and features of biased CPU rendering to the incredible power of the GPU while making it viable and practical for professionals. We also bring unbeatable rendering performance. We can render scenes many times faster than CPU renderers. And we don't just rely on pure GPU power alone. We had to rethink traditional rendering algorithms in order to make this possible. And Panos is going to tell you a little bit about that later. We also have great scalability. We can pack tens of millions of triangles in under a gigabyte of RAM with hundreds of millions on 12 gig cards. And unlike most GPU renderers out there, we did not want limited VRAM to be a problem for us. So we can have virtually unlimited number and size of bitmap textures. And what this means is that artists can render scenes containing terabytes of textures without fear of running out of memory or even crashing. Now we can do this by using out-of-core paging technology for both textures and geometry. Essentially what this means is that all assets don't have to fit in VRAM at once. And we also have built-in UDIM UVTILE texture support. This allows artists to efficiently texture tiles without having to rely on complex shader node graphs to do so. And of course, with simpler shader node graphs, you can get better performance too. So, some features that we implement that are not usually found on GPU renderers are a flexible and easily expandable material system with automatic translation of DCC shader nodes. Now, we wanted artists to have an almost plug-and-play type experience with Redshift. And of course, with more nodes to play with, there's more artistic shading control too. And we also offer multiple biased accelerated GI modes for diffuse bounces and caustics. And these modes are fantastic for getting noise-free results and fast. But they also have to be flicker-free to be viable for animations. A lot of R&D went into this, and we think we cracked it. And we also have full samples control for noise cleanup. This is for primary and secondary rays. This means artists can effectively tune how quickly noise is cleaned up for like reflections, refractions, and shadows, etc. And some other features that we support are importance space volumetric scattering, vector displacement mapping with tessellation with crease support, many object visibility flags, light linking, shadow linking, compositing features such as matte shadow, multitudes of AOVs, and deep EXR support, and many more features that are too many to talk about here. So we're still new to the game, but our customer base is growing. We've been used for ArchViz, TV commercials, and even some Hollywood movies. And before we continue to talk about the more technical stuff, I'd like to show you a quick demo of some of the work our clients have done so far. Like first up is an ad done by a company called Glassworks. We're huge fans of theirs, and I hope that this can demonstrate why.
Dear friend of mine, what do I get you this time? A tablet, a month in a spa, a festive banquet, or a brand new car? I just couldn't decide, so I gave you a card with a dream inside. Put a National Lottery scratch card in a card this year, and you could give someone a life-changing Christmas. Play makes it possible.
Wasn't that lovely? Okay, and the next ad is also by Glassworks, and this is a great demonstration of compositing live-action footage with CG.
Let's move, little stranger. Show me secret scenes. Love can be like bonding. Seduce me once again. Burning like an angel who has heaven in reprieve. Burning like the voodoo man with devils on his sleeve. Won't you move with me in my world of fantasy? Won't you move with me? Ritual fertility.
Okay, and all the cloth and everything was obviously rendered with Redshift, just in case you were wondering. And this next ad is really clean, really slick. We think it's really cool. And finally, this is the work of one guy in his own spare time, and we just think this is amazing. The detail is just incredible. There are no tricks here, no cards in the background, just billions of polygons. It's sheer madness. Short but sweet. And if you want to see more of that stuff, he's uploading new footage all the time, and we've got it playing at our booth. Okay. Next up is Panos. He's going to tell you about the technical stuff. Thank you.
Everybody hear me? I think they do. Alrighty. So we're going to talk about the challenges of developing Redshift. This is like the slightly more technical, slightly more boring part of the presentation. So the first technical challenge had to do with implementing our out-of-core technology. So I mean, you've already heard like some other guys. Most of you know what out-of-core is. It's basically a technique for allowing the GPU to address the CPU memory in case the scene is like too complicated to fit in GPU memory. So Redshift does like out-of-core data access for geometry and textures. The way that it works is actually like really simple. We essentially, the GPU marks bits of memory that it needs, like to do ray tracing or texturing. And if something is like not already in the texture cache or the geometry cache, it creates like a list that the CPU uses to fill that memory. So, I mean, you probably heard like with the other presentation, I think the Chaos Group one, I mean, they sort of like did a little bit differently, but we found that that was like the most performing solution, at least for Redshift. Alternatives actually included using like direct CPU memory reads, but unfortunately, due to some like technical limitations, we didn't go there. Like one of them that was supported for all GPUs that Redshift supports was unified virtual addressing. Unfortunately, that one requires pin memory, so if you have like a scene that uses like tons of textures, you could actually run out of pin memory. And as we all know, if you allocate too much pin memory, then the rest of the system like starts slowing down. Like more recently, unified memory was introduced, but unfortunately there were two problems. One of them is that it wasn't supported by all GPUs that we want Redshift to support, and the other one, it doesn't really work like a cache, which means that you cannot have like a buffer that's actually larger than what the GPU allows. So in the end, like we designed our own like caching system, which, as described, was the GPU marking certain memories and then the CPU uploading those memories. Now the problems is the fact that basically you have like to stall like the execution, you have to stall ray tracing, and you have to stall like texturing. To do that, for us, it was important to actually do that because not only out-of-core for us doesn't just mean uploading the data, but it also means loading the texture on demand or constructing geometry on demand, which I'm not sure if any other GPU renderer allows that. The other problem, of course, is like WDDM overheads. Like every time that you have to communicate any data between the CPU and the GPU, unfortunately, there is like a little bit of an overhead, and that can add up. Tesla Compute Cluster driver mode is like way faster for that. So to avoid those problems, we actually found out that like blocking and the granularity of the data is super important. So for textures, we use like tiled bitmaps. That's what almost every single like renderer out there, you know, Arnold, V-Ray, Renderman. This is like basically the global standard. And for primitives, meaning triangles or hair primitives, we're actually using like local groups. So you know, any triangles or hairs that are actually close in world space are actually close in memory as well. So you know, this kind of like grouping helps out of core. So out of core works really great with textures. We're getting like some really good like cache hit ratios. It turns out that even if your scene is using tens of gigabytes of memory, which some scenes do with Redshift, you don't actually need all that data in memory. I mean, you know, the bitmaps and the tiles mean that you actually need a much smaller working space. Geometry, on the other hand, can cause some problems. You have the problem of certain rays bouncing out and sort of like getting like geometry that's like really far away from the main scene. And we have actually done some optimizations to improve the performance there, and you know, not getting like too many cache misses. But there is more work to be done. So who knows? Maybe next year we're going to be talking about those solutions. So far, though, they do look promising. The other challenge has to do with the material and shading system. So Redshift actually supports like many different like shading nodes. That is partially because we need to support like the shading nodes of the 3D apps. And Redshift has its own shading nodes, utility, math, different like shading modes, all sorts of like different functionality. And the combination of all the shading nodes is basically that there are an infinite amount of combinations. Originally, we thought about a hard-coded system, which probably would run faster, but it would just be like so limiting, and we didn't feel it would be sufficient for the kinds of markets we wanted to target. So originally, the way that we were getting like shaders to work like in kernels was we were creating essentially a code, and we were compiling that code. So you know, like shading connections were essentially just function calls, and you know, just pass it like the NVCC compiler, and we just generate a new kernel. Unfortunately, that is not very practical, because it means that every time the artist moves nodes around, you have to compile, and that takes time. So in the end, we just used function pointers, which surprisingly actually worked. So what we did is every shading node is a function, and then the linking between the nodes is just a function call with a function pointer. So as you can imagine, that bypassed the need for recompilation, and just made the whole experience much more fluid. Now, having said that, CUDA 7 introduced like runtime compilation, so we are contemplating using that as a mode. So because, you know, of course, if you inline code and you let the compiler cut out all the stuff that, you know, like a shading node might not need, that could yield like faster code. So, but again, it will have to compile, so it's a, you know, it's an interesting choice, but we might give that choice like to the user. The other challenge had to do with material blending and layering. As we will describe in a moment, Redshift allows a shading intersection to create like many different rays, like basically like a job queue. And because we do like material layering and blending, we wanted like our importance sampling to work like seamlessly with that. And because that creates some complications, we decided to move the importance sampling technology into the shading system. So that actually provides like some very nice performance benefits. So you actually probably had like the Chaos guys like just 2 talks ago actually talking about how multiple kernels are actually much worse than Uber kernels. Well, with Redshift, perhaps surprising, we found it to be the other way around. So with, as you all know, you can basically write a renderer with 2 ways. You can put all your code in an Uber kernel, or you can launch multiple kernels. With us, we actually had to do the multiple kernels because our out-of-core data access meant that the rendering process has to be interrupted so that the CPU can do loading or can upload data to the GPU. We support also like multiple GI modes, and those kernels are actually requiring certain techniques that work best when they happen like more homogeneously, you know, just doing like point searching. And our shading system is complex enough that it actually required to be like a separate kernel. Now, additional reason we didn't go with an Uber kernel is because we found like quite a few compiler issues, unfortunately, where there were some bugs. The compilation times were significant as well, which inhibited our ability to iterate. And register pressure was probably also a compiler issue. Unfortunately, was uneven. Sometimes we change like a few lines of code, and now we're using like too many registers. So that made us a little bit nervous. So, so the main benefit of actually splitting your work into multiple kernels, where when you do rendering, you have like to ray trace, and then you have to shade. And if you're doing like point-based GI, you have to search for close points on the intersection point. And basically, you have to do like a lot of like different kinds of work. Unfortunately, doing that on the GPU is a really bad idea. I mean, because like divergent branches means that certain like threads in a warp are just idling doing nothing. There are solutions for those things. You can sort. You can actually do like certain like types of rescheduling when you are trying to group work and get like all the warp to do like only tracing or only shading. The problem is that if you try to do that like on an Uber kernel, it can be really complicated, really complex to achieve that. So basically, with multiple kernels, on the other hand, you can try like those different like optimizations that are like case-specific, much easier. And of course, the other benefit was because we split the work into smaller kernels, we have the ability of changing like a small part of Redshift and be able to compile only that and be able to prototype code. Now, the drawbacks is that there are overheads. That's true. I think the Chaos Group guys actually mentioned that as well. There are overheads, and actually, depending on how you manage your array state, you can actually get like you can get into that GPU underutilization problem. However, there are solutions to that as well. If you actually group your work in like in intelligent ways, it means you're not suffering as many overheads because you're not calling the kernels like as frequently, and the same goes with GPU underutilization. So basically, for us, like the continuing goal is to try to generate and submit as much work to the GPU as possible. Doing that means overheads and underutilization are much less of a problem. The other thing, this is perhaps like the thing that differentiates Redshift from at the other end the most, is the way that we're actually generating rays. So typically, the way that like ray tracing works is you shoot like a ray from your camera, and then on the intersection point, you have like a shader that says, shoot reflection rays or refraction rays. So in this particular case, we have like a glossy reflective refractive plane, and we have like, the green arrows are like the reflective rays, and the red ones are the refractive rays. So that's typically how rendering happens. However, that's not the only way that you can achieve that. The other way is to do it like with Russian roulette, where basically what you're doing is you're doing your rendering in passes, and then you're picking like fewer possibilities instead of like, shooting all your reflection rays, all your refraction rays, you just pick like one or just fewer. So for example, in the first pass, the renderer might choose to do reflection. On the second pass, it might do refraction. On the third pass, it might do refraction again. On the fourth one, another reflection, and so on. Now, if you get all those passes, you sum them up, and then you weigh them, you get exactly the same result as the previous one, with a negative that you had to shoot like an extra camera array. So, here we showed like reflection and refraction, but the same technique can be used by any technique that might spawn multiple rays. That includes like, GI, direct lighting if you have multiple lights, or area lights, etc. Russian roulette is great for interactive rendering because it allows you to render your frames sort of like progressively. So, the artists get like a quick feedback. Unfortunately, you have to, because it can introduce like more rays, it's very important to pick the correct rays like on every pass. And there are like many techniques for doing that. There is like, obviously like QMC, there's like Metropolis, there is like all sorts of like techniques there. Unfortunately, those techniques, they don't really work every single time on every single case. And when that happens, you get persistent noise, which requires many, many, many passes like from your progressive rendering to clear. Russian roulette has the other benefit that's very easy. Artists don't need to care about, setting 256 rays for reflections or, 1,000 rays for lights or stuff like that. Just set like the number of passes, and, the higher this number, the smoother and the less noise the rendering. Now, doing things like the Russian roulette way is actually easier when you're developing a GPU renderer, which is why basically almost every single competitor is doing it this way. We chose to do it like slightly differently. We chose to actually allow the renderer to be able to spawn multiple rays out of one intersection point. And by the way, this is how like V-Ray and the CPU version, that is Arnold and other like by-CPU renderers work typically. And the reason why we chose it is because there are actually certain scenes that can clear up faster doing that. And also it allows the artist, if they have like a persistent noisy element in their scene, to sort of like, give more rays to that one, which is like really hard to do with Russian roulette. I mean, not impossible, just harder. Having said all of that, Redshift can also do Russian roulette as well because we support progressive rendering. And also, Based on ray importance, you might choose to do like few rays anyways. I mean, there's no point like shooting tons of rays, you know, on the 10th recursion of rendering, for example. Now achieving that though is actually like really hard. Like the trivial solution is, what's hard about it? Just put like a loop that spawns rays. That is actually really hard because if you do that, then you might get like really bad coherency. You might get, for example, a shader that wants to do like 1,000 reflection rays, and the next intersection might want to do no reflection rays. So that actually means like branching incoherence and bad performance. So what we did instead, actually we chose to use like a job queue. So what this means is that when there is a material intersection, the shader has the capability of actually spawning work for the next recursion, which is actually processed in parallel. So instead of like having loops, we have, we basically expand the work, and then, the next time around, the next recursion, we process this work in parallel. And this is actually like very important, like for achieving like material layering, which by definition means spawning multiple rays out of one material intersection, and multiple lights as well. I mean, many of the GPU renderers out there, if you have a scene with 200 lights, on every intersection they will pick one, usually randomly. And as you can imagine, there are certain cases where, they will not pick the right one, and you will get persistent noise. So it's actually better to just, bite the bullet and just like shoot rays towards most of them or all of them, even in some cases. The downside is that it's actually much harder to manage memory. But in the end, like the performance meant it was worth it. So the final challenge, which I'm going to go pretty quickly, has to do with the CPU performance. Perhaps surprisingly, the GPU cannot do everything by itself. There are extraction times, disk network, certain tessellation, like even saving images to disk can be slow with DPXR. So, and like the next graph actually shows, how that can happen. You have like your CPU processing, which might take 1 second, the GPU takes 4 seconds. Even if you have like 4 GPUs working in parallel, your CPU won't become any faster. So it means 4 GPUs doesn't mean 4 times faster performance. And the solution there is obvious, just speed up your CPU processing as much as possible. So we have actually spent like quite a bit of time optimizing our CPU parts of the code because we don't want the GPU to be bottlenecked by that. We're caching and reusing data so we don't extract the scene every time the user hits like preview. And we always try to use the GPU more during like those pre-processing stages. The other solution is to be rendering like a few frames at once, so that actually changes the ratio between how many CPUs and how many GPUs you have in the system. So rendering like, instead of rendering 1 frame with 4 GPUs, why not render 2 frames in parallel, and every frame getting like 2 GPUs. So in that case, you're actually forcing multi-threading, even on data extraction might not have been multi-threaded, which sometimes is the case because of, SDK, on XSI, for example, we cannot do that. But it can consume more memory, so that's the drawback, I suppose. So what's next for Redshift? So right now, Redshift already supports like Maya and Softimage. 3D Studio Max is in development, and there's going to be like more DCCs as well. Linux support is actually also in progress. Ray marching, which is like volumetric, to get smoke, flame. I mean, that we have actually done like really good. We don't have like any images to show so far, but it's actually working like really nicely already. Single scattering to complete like our subsurface scattering technique. We want to support like more third-party hair solutions in Maya, more BRDFs like GGX, which everybody loves. Redshift already does like a ton of different AOVs, like raw, diffuse, lighting, specular. Like basically, we do all of them, but users have requested custom AOVs as well. So we're going to be adding those too, so they can make their own AOVs. And we also want like a shader SDK, which might open the possibility for OpenSL and more optimizations. Alrighty, so yes, that was the presentation. If you have any questions, please don't hesitate to send us like an email at info@redshift3d.com, or meet us after the presentation at the welcome reception or at the GTC Expo Hall at the booth 112. Thank you.
Congratulations.
Thanks.